So I went to the blue screen early, so everybody online's probably thinking, where's the screen? So welcome, guys. What is it Dave said? It's week 4, so we're going to talk ventilation. So for the online people, I'll try to go over and take some photos in the lab, but we're actually going to go over today and do some calculations. So for you guys, what do you know about ventilation? Tell me what ventilation is. Where would you use it?
Air conditioning.
Air conditioning, absolutely. What's that do? Makes things cooler, right? Cools the temperature down. It's funny because we're going to do thermal stresses today. Hot and cold, so awesome. Where else would you use ventilation, Dave?
Anytime we need to exchange air in one compartment.
Okay. Very technical, precise definition. So look at it again. Or maybe we want to remove contaminants.
Exchange air. Whether
There you go. That's interesting. So guys, here it is. Here's your two types of ventilation. Dilution and local exhaust. So which do you guys prefer?
Depends on the situation.
There you go. That's the answer. It can be either one. So sometimes when you're looking at ventilation, you need to know the difference between the two. So here's your things to consider. And this is the easy part of the lecture. What do I want to consider? Basically the source. In other words, what's being generated, what's going on. And then the other side to that, as you look at it, you need to also consider characteristics of the compound and characteristics of the employee. So if you guys notice, it's kind of all three. We've got to know the emission, how it's going to behave, how the air's moving in the room, and also the employee, what they're going to do. Kind of important. You guys have seen this before. You will see several questions, and I always show this for the live guys, and this always stays in here. So here is your gas law, and you can see it. PV equals nRT. Well, I don't want you to just know that. I want you to know what is 1 mole at standard temperature pressure. You guys see my box I made up? Don't you love this? And the other thing you may want to know, you guys have already used 22.4 liters. What's that equal to? And the last thing on my box, what is 1 mole of oxygen? What is it, guys? 32. Yeah, what's 1 mole of helium? I wondered what they put on there. 4. There you go. So there you go, guys. Kind of give you that one too. And then 1 mole, what's it equal to? Basic science. I know we did that in the first week, but I love my box, guys. That's my favorite little box. By the way, if you ever want one of these, they are available. Science First Mole Box. I love it. I know everybody will run out and buy one now. I do own stock in that company. No, I really don't. I wish I did. So anyway, that's all you need to definitely understand your normal temperature pressure, standard temperature pressure, and your air densities. So, what do you guys see here? How much does 1 cubic foot of water weigh?
62.4.
Yeah, how did they calculate that? What about the other thing? What does 1 cubic foot of air weigh? Yeah, so let's talk about how they did this. The other thing too, remember air density varies with temperature and pressure. So as 70 degrees F, 29.92, we used to call it 29.9 inches of mercury, basically is standard temperature pressure, but it changes a little bit as it goes up. Here's how it changes, guys. It's called a density factor. It's reviewed in Stewart's. You've got a couple of problems in your book on that, but I wanted to make sure that you saw the actual formula. And you're going to notice I did it in Rankine. You will see different things that will happen for temperature in Rankine. So, here's your example. You have this. what is the density at 100 degrees F at 27.82 millimeters of mercury? So first question, is that less than or equal to the normal pressure? Is that less than 29.9? It is less than. If you notice that, so what's it going to tell you about your density? It's going to be less than 1, because that's a fraction. So here's a simple calculation to determine the density of air at that particular condition that I gave you in the problem. You have that one in there. So here's your basic, wonderful, you got to know this to go anywhere, okay? Airflow. What is V?
Velocity.
What do we usually deal with it in?
Feet per minute.
Yeah, that's what you deal with it in. What do you guys? There you go, thank you. You guys have got to think both ways, okay? Because even though you may be working in an imperial system, you may go to the metric and vice versa. So I will warn you, and this is for going out there, occasionally I'll make you do conversions. Now, whatever you're comfortable with, do it. I have international students that I love dealing meters per second, but when I do calculations in North America or England, I always have to do it in feet per second. So keep that in mind. That is your velocity. What is your area? How do we get an area? What's the area of this room? How would I get it?
Length times height times width.
There you go. And what's that? Square feet. There you go. So your area, and you can see the diagram. Basic equation, right? Here's something you need to understand, and this will not go well with you at first. It's called conservation of mass. So my question, V1, so the velocity of 1 times A is equal to the velocity of 2 times A2, or area 2, and the velocity of 3 times A3. What are all those, what does this equation say? What is the cubic feet per minute in all 3 of these regions? Yeah, it's kind of a tough concept, and I want you guys to understand it doesn't make sense because you're first going to look at it and go, wait a minute, that's bigger, but it always, again, your conservation of mass.
Okay, just the pressure will be different.
There you go. But it's hard. Your first thought is the bigger the area, that's going to slow down. Or that's what I always thought. It's just a good concept. Air changes per hour. So what do you first have to calculate? If someone, namely a professor for industrial hygiene calculations, would ask you, I have this cubic feet per minute Q. How many air exchanges do I have? Well, I better tell you the room size. So how would you solve this one right here? What do you guys think you'd have to do?
First solve for the
Yeah, what's the volume? 40 times 10 times 8, right? And that would give you your volume. I didn't give you the Q. So that was kind of your local exhaust ventilation. Let's talk about some dilution, and we'll go back. Dilution ventilation. I want you guys to see one thing that you'll see over and over again. Dilution's used for non-toxic. Why would we worry about whether it's toxic or non-toxic? What's dilution? If you guys are handling a chemical right here in the middle of this room, what would dilution do to that chemical or compound? What's it going to do? Yeah, it's going to basically, right now we got dilution coming into this room. What happens if there's a powder or a chemical or something here? What's the ventilation going to do? Yeah, just spread it all out. Why would we worry about we only want to use it on relatively non-toxic. What are we doing with that? Yeah, we're sending it out. Everybody gets some of it instead of controlling it right in place. That's an important part too. Gases, vapors, respirable aerosols, you guys can see all the requirements. Replacement air has got to be less contaminated. So here's kind of an example with benzene. And I wanted you guys to see this. This is vapor generation. So if you look at the molecular weight of benzene, 78 grams, pounds per mole, 78 pounds. If it's evaporated in 387 feet at STP, what is the Q? And if you look at this, this is the formula you will use, and this will actually give you the volume of air. So I want to go back. I want you guys to see what we're talking about. We've got 1 pound mole. We're putting it into the room. Again, what is the Q, or basically the volume of air in cubic feet per minute. Now the density will also play into it. If in a problem they don't give you the density, what do you get to do? Yeah, assume 1. Okay, don't get wrapped around the axles. If you're using a formula, it has a density in it, and you're trying to correct it. So there's your formula for emission rate. Here's also one that you guys will see, and I want you to again look at the formula. This is for dilution volume. Basically, the recommended dilution volume, when you go through that, will be related to this wonderful thing called a mixing factor. If I don't give you a mixing factor, what happens? Yeah, assume 1, assume you don't have to worry about it. And then, what's this CA? What would you guys use for that? Acceptable exposure in ppm. Where would you go for that? Yeah, the ACGIH or OSHA PAL. And I will always, again, in the problems, tell you what you need to use there for your acceptable, okay? But in the absence of data, you'll go use the standard, the regulatory standard, okay? Again, formula, it basically, this tells you how much the volume of flow of air that you're going to need. So it's very valuable. Dilution ventilation, again, normally air quality, indoor air quality, contaminants are relative non-toxic, and that's the same slide we used. Here's your decision criteria. I want you guys to think about what we're saying. When would you use dilution volume or dilution ventilation? Yeah, non-toxic. And you're going to determine what is an acceptable concentration. You're going to study the emission source. You're going to look at evaporation rates, and all the way down through there till you estimate how much volume you're going to need. These are the steps. Guys, again, this is what ACGIH, it's what all industrial hygiene decisions are made on. Okay? So again, back to this wonderful vapor generation. So you guys have seen that. You've seen all the dilution. I just wanted to go through the mixing also. So as you go into this, here we're going to trade. We've been in dilution volume. Now we're going to go to LEV, or local exhaust ventilation. Okay? So when I say that, suddenly you should kick mind. So what were we doing on dilution ventilation? How were we protecting people? What was happening to the contaminant?
Spreads out so it has.
Yeah, it's not as dense, doesn't have as much mass. What are we trying to do with local exhaust volume?
Remove it.
Or ventilation, local exhaust ventilation, remove it. That's the difference. One spreads it, one removes it, okay? You'll hear the term LEV versus dilution. Now, I want you guys to understand, most of the time, you will use local exhaust ventilation, LEV. However, there are cases, and I've been in them, where we don't care. If it's relatively non-toxic, and we don't care that we spread it out in a room, guess what? You can use that. And there's examples. But here are your local exhaust components. And you guys, we were just talking about earlier, hoods. Where do you normally see hoods?
Labs.
Yeah, laboratories. Where do you normally see ductwork?
Every space.
Yeah, every space. Scrubbers, usually environmental controls. A lot of people that take this class are worried about environmental control. They tell me, what does this have to do with environmental? This ventilation part, the calculations you guys are going to do are exactly what you'll do for environmental controls too. Same thing. Fans and motors, we'll talk about that, and also your stack. So we'll do a little bit of later on community. So here's your air pressure. It doesn't matter how you want to do it. I actually like, again, the Imperial 14.7, 29.9, 760 millimeters. You guys can see that they're all the same, depending what you're doing. So, at sea level, and you guys, in a lot of my problems, you'll notice I'll give you 760 millimeters of mercury. This is what I'm talking about at sea level. It's 1 atmosphere, you'll know too. However, what happens when you go to an altitude of 500 or 5,000 feet? What happened? What did it go down to? So here's my question to you guys. There's a city in the U.S., Denver, Colorado. They have a nickname for this city. Do you guys know what it is? Yeah, Mile High City. That's right, football. I could figure somebody would say John Denver, or not John Denver. Who was the Broncos quarterback?
John Elway.
John Elway, thank you. Man, that was terrible. But anyway, what happens if you're at Virginia Beach, Virginia, sea level, and you go to Mile High City? What happens to, again, the air pressure? There you go. To probably about 630 millimeters of mercury. So do you understand that pressure drop? Higher, pressure goes down. Got it? Just an example. Static pressure. This is something we're going to talk about in ventilation. This is a concept that you guys will need to think about in your pressure, and you'll have some problems on this. Static pressure, perpendicular to the direction of flow. So it's always negative if it's inward, positive if it's outward. And you have some examples in your book that you can look at. But here's your big thing. What is velocity pressure? What's kinetic motion? What do you guys think kinetic energy is? If I say kinetic motion or kinetic energy? It's moving. Yeah, it's moving. It's the wind. So again, it's positive in the direction of air motion, and it's proportional to the air velocity. And then your total pressure. So what's your total pressure equal to? Yeah. So you're going to see it written like this. And that's an equation you guys need to see, and you'll see it on some of my slides. Why is that important? So if I give you the total pressure and I give you the static pressure, what can you solve for? There you go. And you're going to see another formula where we actually use to solve for velocity pressure if you know other components in there. But I just wanted you to see that. Again, I've got a couple in another presentation you guys will see, I think. I'll show you where the fans are set up, how you determine static pressure and velocity pressure. But just keep in mind, the two of those together equal the total pressure in the vents. And here's the example you can see. So, I want you guys to notice in this example, they are pushing air through here, and if you notice on this side of the fan, and this is a fan, it's a negative. So it's negative, this is positive. Think about it. Why is it negative? What's happening to the air? Yeah, it's sucking it in. It's negative. This, it's pushing it positive. That's a terrible explanation, but again, how do you visualize it? Pulling negative, pushing positive. That's how I think about it. Again, I tried to give you guys exactly a manometer with water and how you measure static pressure. If you notice, the atmospheric pressure is 407. You got 406 inches going through there. There's a difference of 1, which is your static pressure. So again, that's kind of how this works. So, what do you think's happening here with this one? Guys, I'm not an artist, so sorry about the bad diagrams, but it gets the point over. So on this side of the fan, what is it? And positive again. So what's the static pressure? 1 inch, right? Notice that's the difference. What's the total pressure? So what does the velocity pressure have to equal? Yeah, 0.7. What I tried to do with this diagram is give you, this is giving you velocity pressure, this is total pressure, and this one's giving you static pressure, okay? So I tried to give you a visual representation of what we're measuring. I know this is one of those concepts that's like, well, it doesn't make sense. Yeah, think about it, it does. Your total pressure is static pressure plus vapor pressure. Now, for those that are like me, that like a simple chart, here's your simple chart. When I say upstream, what do I mean? The air's coming in this way. What's upstream? Yeah, before the fan. I need you guys, and I will do this. There are questions you'll go through where I'll talk upstream, downstream, and it'll confuse the heck out of you if you don't keep this little chart. Now here's what I want you to really notice. What happens here? So what is the total pressure, the static pressure, and the velocity pressure? What are the signs on them? Negative. So that's upstream. Does that make sense? Remember back to this one? How these are measuring and what's going on there. So use that. What about downstream once it gets out? All positive. There you go. So it's just a good chart to go through. Here's kind of some of the assumptions too with ventilation. Static pressure is 0 outside the system, and this is losses in the duct. Static pressure is negative prior to the fan. I've hit that one. It's as you move closer to the fan, what happens? The negative goes up. It moves quicker, it's faster. Ducts are more likely to collapse inward near the fan, and static pressure is positive after the fan. And it will decrease. You guys think about it, if you have a fan pushing things through ventilation up to a stack, what's going to happen? It's going to slow down as it gets near the stack. Clear as mud, right? You guys just love ventilation. So here's the problem. We know this. Friction losses. The higher the velocity, the greater the loss. In other words, the longer the run, the greater the loss. If you guys think about this, whether it's water, air, anything, the longer it goes down through there, the more static it's going to create and more friction it's going to create. So the smaller the diameter, the greater the loss, and again, the more turbulent, the greater the loss, and the more turns you have, the greater your loss. So it's trying to help you with design, and the rougher the interior surface, the greater the loss. That's why if you ever look at ventilation, it's all smooth. So how do you guys feel about ventilation? A lot of information thrown at you, right? So what I'm going to try to do, if you guys are okay, we're going to walk over to the ventilation lab. I'm going to pause this and we're going to walk over.